Dear students, welcome back again. Today's topic is the electromagnetic waveguide, which is the section 4. The title of the topic is rectangular waveguide. We have done last time the parallel conducting plane waveguide. Now what is now a rectangular waveguide? We are going to discuss. What is a rectangular waveguide? A rectangular waveguide is formed by placing two more conducting planes on the open side of two parallel conducting planes. Such a rectangular tube is called a rectangular waveguide, as shown in the figure below, figure 1. So last time what we had, now we place the A along the x-axis, the similar two conducting planes were there. Now we place two more conducting planes now on the open ends. These were the two open ends. So the x was 0 to A, that was taken the last time, but we now have another set of two plates, conducting plates, which are placed at a distance B. It's not necessary that A is equal to B. A might be different than the B. So we take again the electric field function and the magnetic field intensities, electric field intensity and the magnetic field intensities as a function of e⁻ minus gamma z with their obviously corresponding amplitudes Ex0 and Hx0. Similarly, Ey0 and Hy0. So this figure is we are having now the A along x-axis and B along y-axis, and the Z is the propagation, the signal which is coming out of the waveguide, rectangular waveguide along the Z direction. The rectangular waveguide and all such similar ones provide an alternative transmission line at ultra high frequencies for the transmission of electrical energy. Any wave propagation within such a waveguide must satisfy the Maxwell equations and must also satisfy the boundary conditions. Those boundary conditions imposed by the walls of the waveguide. Now let us consider A and B be the plate separations between the parallel conducting planes along x and y axis respectively. To determine the field configuration in the guide, Maxwell equations are solved subject to the appropriate boundary conditions, assuming that the walls of the guide are made of perfect conductors. The tangential components of E and normal components in this case will be, and the normal components of H are 0 at the surface of the conductors. The tangential component of E and normal components of H are equal to 0. At x is equal to 0 and x is equal to A. At x is equal to A, you reach to the surface of the plate. At x is equal to 0, you are also at the surface of the plate. Similarly at y and B, at y is equal to 0 and y is equal to B. The Maxwell equations for electromagnetic wave traveling in the waveguide filled with the air. Now the medium inside the waveguide is air. Being a non-conducting medium, are given as, those equations are given as curl of H is equal to epsilon delta E by delta T, and curl of E is equal to minus mu delta H by delta T. We mark them 1 and 2. Since the E is equal to E0 e raised to power j omega t, which is the space and the time dependent two parts. Similarly, H is equal to H0 e raised to power j omega t, but H0 obviously again the space part will also have a certain the function of pattern. So taking the differentials of these E and H, we have delta E by delta T and delta H by delta T values, and putting those values back into the equations 1 and 2, we get curl of H J omega epsilon E, curl of E is equal to minus J omega mu H. Taking the curl of the both sides of the equation 3 and 4 and applying the vector identities. For first, that is vector identity curl of A is equal to divergence of the gradient of the divergence of A minus del square of A. So what we get with the both equations as the del square of H is equal to minus omega square epsilon mu H, equation number 5, and del square of E, which is equal to minus omega square epsilon mu E, equation number 6. Since the divergence of E is equal to 0, because we have the charge density is equal to 0, the medium within the guide is air, and which is non-conducting, so that is equal to 0. So also divergence of H or divergence of B is equal to 0. Putting those, we got these two relations. Now expressing equation 3 and 4 into component forms, that is we can take the equation that is 3 and 4, which is the curl of H. It has its x, y, and z components, and there are the corresponding Ex, E, Ey, and Ez. This is the Ey, this is Ez, and this x component. So this is the y component, this is z component, this is x component. Equation 7, 8, and 9. Further, similarly, for E, we have got Hx, Hy, Hz, comparing the both sides over there and the corresponding the unit vectors, which is this is the x component, delta Ez by delta y minus delta Ey by delta z, and this is the y component, this is the z of the curl of E. This is the x component, this is y component, this is the z component. And similarly for equations 5 and 6, we have the del square of E. Now it is expressed in terms of comparing in or expressing at the moment del square of E by x square, y square, z square, delta by delta z square with the partial differential, which is equal to minus omega square epsilon mu E. Question number 13, or similarly del square of H in its component form, the x, y, and z, which is square of these partial differentials, is equal to minus omega square epsilon mu H. Since the gamma is equal to alpha plus j beta, we have already defined that. Let us now take the electromagnetic wave travel as e raised to minus gamma z with e raised to j omega t. So space-time dependent parts, then we have E field is given by E naught is for minus k minus gamma z times that when we multiply it is added in the powers to the exponent plus j omega t, and H is equal to H naught e raised to the power minus gamma plus j omega t. Now we have E and H plane wave components in the waveguide. Now we express those. The Ey is E naught y e raised to minus gamma z, Ex E naught x e raised to minus gamma z. Over here we should have, okay, the E here correction made. The Ex E naught is equal to E naught x e raised to minus gamma z. Similarly, Hy is equal to H naught y e raised to minus gamma z. The space dependent parts, which are the space dependent parts of the electromagnetic waves. Now putting the delta Hy by delta z is equal to minus gamma Hy from equation number 7, we have the delta H in equation 7. We put delta Hy by delta z is equal to minus gamma Hy. In equation 7, what we have, the delta H z by delta y minus delta Hy by delta z is equal to, this is equation number 7, j omega epsilon Ex. So since we have the hy, and we differentiate that hy, we have already defined hy over here, so we will get the minus gamma hy. We put that in this equation number 7. We get h delta hz by delta y plus, because the minus come from here, so minus we get plus. The value we put the delta hy by delta z, which is minus delta x by delta y. Here, sorry, delta hz by delta y plus gamma hy is equal to j omega epsilon ex. This is equation number 15. Now from equation 8, similarly we put the delta x by delta y value, so we get this is equation number from equation, this was equation 8. Now from equation 9 we have delta hx by delta z minus delta hz by delta x j omega epsilon. Since we have already defined the h and hx, and that delta hx by delta z is equal to minus gamma h of x. So it's a mathematical straightforward, very clearly written steps. You can see and follow them. So what we get, delta, here we get delta z by this one, delta z by delta x. We put the value of delta hx by delta z, rearranging the term, when we get delta hz by delta x plus gamma hx is equal to minus j omega epsilon ey, equation number 17. From equation 10, putting the delta ey by delta z is equal to this, minus gamma ey, and delta ex by delta z is equal to minus ex. So gamma ex we have, this is, you see, ey, and this is ex. So what we have, the delta ez by delta y minus gamma ey. So every reference is given. Equation number 10 is there. By putting these values we get equation number 18, minus gamma ey, so is equal to minus j omega mu hx. Similarly, in equation 11, putting the delta ex by delta z minus is equal to minus gamma ex, we get this relation, equation 19, which is the delta ez by delta x plus gamma ex is equal to j omega epsilon j omega mu hy, equation number 19. Now from equation 12, we have the delta ey by delta x minus delta ex by delta y. J is equal to minus j omega mu hz. Now equation 13 and 14 expressed for the electromagnetic wave traveling in the positive z direction as delta 2ez by delta x square. These are the equations which you remember, the del square of E. Now delta 2e z by delta y square plus, that is the delta 2ez by delta z square has been now replaced by gamma square ez is equal to minus omega square epsilon mu ez. Similarly, for h field along the z is given by delta 2 hz by delta x square, and similarly ignore the second differential square of the second differential of the y plus gamma square hz equal to this equation number 22. The above set of equations can be rearranged to get the hx. Okay, so from equation 17, delta hz by delta, which this equation we can get delta, if you go to and see 17, delta hz by delta x is equal to minus gamma hx minus j omega ey. But from equation 18 we have ey value, that is the ey value. So putting that value into equation number 23, we get delta hz by delta x, rearranging all these mathematical terms. Here remember we get the gamma square plus omega square epsilon mu, we put that equal to some value h square this time. So that is, after rearranging we get hx is equal to minus gamma by h square delta hz by delta x plus j omega epsilon h square delta ez by delta y. So similarly we can find for the other field components Hy will be equal to this term, just 25. Ex, we will be having the only thing, the rest will be E will be replaced with Ez over here, and Ex, whichever that the partial differential we will take, rest will be having the similar equations. Here in the E case we will be having here E and here H. In the H case, here we H, here E. So this is these things only we replace, rest will be the same. Similarly, Hy Ey is given by this relation, equation number 27. So where H square, obviously this is H square, let me correct that. H square is equal to gamma square plus omega square epsilon mu. It can be seen from the equation 26 and 27. 26, 27, that if Ez and Hz are 0, then all the field components vanish. Thus, for propagation along a waveguide, there should be at least one of the Ez or Hz components present, so that wave can propagate. So the boundary conditions to be satisfied for the rectangular waveguide are Ey is equal to Ez is equal to 0, at x is equal to 0, and at x is equal to a, Ex is equal to 0, Ez is equal to 0, at y is equal to 0, and y is equal to b. Similarly, the similar for conditions for the H as well. So thus the equations 24, 27 describes the field configuration inside the waveguide. So that means these equations which we have worked out, these are the final equations we have taken. So these equations, that is the Hx, we have got here Hx, Hy, Ex, Ey, they describe now the field equations. Equations 24, 27 describe the E and H field configuration inside the waveguide. So students, we reached to the end of the topic. Inshallah, we will meet again next time with a new topic. Till then, goodbye and thank you.